Hi student, let us solve the following problem. The statement of the problem is this. They say a concrete highway curve radius 70 meters is banked at a 15-degree angle. So what is the maximum speed with which a 1,500 kilograms rubber tire car can take this curve without sliding, right? So we want to calculate here the maximum speed of the car, right? Why taking the curve? So overall now here is B maximum. Now to solve this problem, we're gonna, instead of using the X and Y axis, we're gonna use a system with the axis RTZ. So radial, tangential axis, and also a Z axis, right? So in this case, the radial axis would be here. It's gonna be a horizontal axis in this case, pointing toward the center of the curve. The z-axis, right, which is vertical, and we have then the tangential axis, which is in the plane. There is perpendicular to the screen of my computer or to your notes, right? Now, which are the forces acting here? We have the force of gravity, of course, which is equal to a product of the mass times the gravity. And we have a normal force, which is perpendicular to the surface of the road. We have also a force of static friction, which is parallel to the surface of the road, right? This normal force, we have components on the z-axis and on the r-axis, right? So we are now going to represent the component of the normal force on the z-axis, which is this one, and we will have another component that will be the component of the normal force on the radial axis, which is this nr. So we have m sub c, which is the component on the z-axis of the normal force, and m sub r, which is the component of the normal force on the radial axis. Exactly, as with the normal force, we have that the force of static friction, we have components, right, also on the r-axis and on the z-axis, right? So we're going to have here a radial component of the force of static friction, which is pointing to the left, and we have then a z component of the force of friction, which is F sub c here, force sub S sub c. This is for sub S sub r. So the radial component of the force of static friction, and the in the other case the z component of the force of static friction. Let me just clarify here, which are the sub-indexes, right? So this is F of force, static, so S of static, and then we have Z because it's the Z component, and it's this force, that I am pointing here with my mouse. So what else we know? We know that the force of static friction will be equal to the product of the coefficient of static friction times the normal force. Based on the information provided by the textbook, we have that in this case, for rubber on dry concrete, the coefficient of static friction is going to be 1, right? Rubber on dry concrete, coefficient of static friction will be 1. So with that information, then we're going to solve our exercise. So the first we're going to do is to make a sum of forces in the z-axis, right? So I say that the sum of the forces in the z-axis is equal to the z component of the normal force, so this one, minus the z component of the static friction force, which is this one. Is negative because it's pointing downward over here, right? Minus mass gravity, which is just the force of gravity here, and all this will be equal to 0, right? Because there is no possibility of motion, in the vertical. So now the z component of the normal force will be n, also normal force, n of normal, cosine of 15 degree, right? Because it's the adjacent side to the angle of 15 degree we have here, minus, now the z component of the force of static friction will be mu sub s times the normal times the sine of 15 degree, right? Because this component, right, is just opposite to the angle of 15 degree, right? Minus mass times gravity. So now we're going to solve for the normal. Of course, we know that the coefficient of static friction based on the information provided with the book, we found that is 1. So we have that n times cosine of 15 minus n sine of 15 minus mass gravity is equal to 0. We bring the mass gravity to the right and we factor the normal force out as common factor, so we get n times the cosine of 15 degree minus the sine of 15 degree is equal mass gravity. Of course, now we're going to divide by the factor cosine of 15 degree minus sine of 15 degree to isolate the normal force, and we're going to get, the following expression that say that the normal force is equal to the quotient sorry, of the mass times gravity divided by the cosine of 15 minus the sine of 15. So the next we're going to do now is to make a sum of forces in the radial direction, right, along the r-axis, right? So which are the forces we have in this case? We have the radial component of the normal force, which is this one pointing in the direction of the r-axis, plus the radial component of the force of static friction, which is this one pointing also in the direction of the r-axis, and this will be equal to the product of the mass times the centripetal acceleration, because as he's moving, in a circular motion, this car basically, there will be there a centripetal acceleration, so the net force will be equal to the product of the mass times the centripetal acceleration. So we know, of course, that this mu sub s is 1 based on the information given by the book. We're gonna then get a common factor n here. So we get a common factor n. So we say n sine of 15 plus n cosine of 15. It would be n times sine of 15 degree plus cosine of 15 degree. And this will be equal to the product of the mass times the centripetal acceleration, right? That is what we have just in this part. Now, we're going to get this expression we have here for the normal, and we're going to plug it into this other equation. So we're going to replace, this normal that we have here by expression, which is mass gravity divided by cosine of 15 degree minus sine of 15 degree. So when I do that, I will get that mass gravity sine of 15 plus cosine of 15 degree divided by cosine of 15 minus sine of 15 degree is equal to mass b squared over r, because the centripetal acceleration is mass b squared over r. Well, centripetal acceleration is b squared over r, but we have the product with the mass in this case. We're going to cancel the masses here. So we're going to have that the gravity times the sine of 15 degree plus the cosine of 15 degree divided by the cosine of 15 degree minus the sine of 15 degree will be equal to b squared over r. We solve for b squared, so we pass the r multiplying, so we get that b squared is rg times sine of 15 plus cosine of 15 divided by cosine of 15 minus sine of 15, and now we apply square root, and we're going to have that the speed would be the square root of the radius times the gravity times the sine of 15 degree plus the cosine of 15 degree divided by the cosine of 15 degree minus the sine of 15 degree. Now we substitute the radius by x value, which is 70 meters. We substitute the gravity by x value, which is 9.8 meters per second square. Of course, these times sine of 15 degree plus cosine of 15 degree divided by cosine of 15 degree minus sine of 15 degree. So when we perform all these operations and we find the square root, we're going to get that the speed in this case is approximately 34 meters per second. So when we have a band curve, at 15 degree angle, we're going to have a maximum speed that is going to be higher, than the example that is in the book for pretty much the same conditions, except that the angle was 0 degree. So the maximum speed is just higher than in the other case where the angle was 0 degree. Of course, because in this case the radial component of the normal force is going to contribute, with the keeping the car on track, right? So with the net force. So thank you for your attention. I hope the exercise was interesting for you, and just please support my YouTube channel. Thank you so much.